Good evening, and welcome to the Late Lab. It's wonderful to have you here. Before we disappear into tonight's quiet mystery, I'd love to know where in the world you're listening from. Perhaps you're beneath warm blankets, watching the last lights of the evening fade beyond the window, or resting somewhere peaceful while the rest of the world slowly grows still. Wherever you are, I hope you feel safe, comfortable, and ready to let your thoughts drift a little further than usual. If these calm explorations help you unwind, sleep, or simply spend some gentle time with the stranger corners of science, a like and subscribe helps this small channel continue its journey through the dark. And to those of you already here, returning night after night, thank you. Your support is quietly appreciated more than I can say. Tonight, we're going to look into what seems to be nothing at all. Empty space, a perfect absence, a silent gap between everything that exists. And yet, when physics looks closely enough, that silence begins to reveal a hidden structure. Fields remain. Energy refuses to vanish completely. Even the deepest vacuum may carry faint traces of activity, as though the universe is never entirely able to become still. I'll try not to make nothingness sound too lively, although there is something rather beautiful about the idea that even when every visible thing has gone, reality itself remains behind, quietly waiting. So settle in, let the room grow soft around you, and allow the silence to deepen. Why is empty space never truly empty? A vacuum sounds, at first, like a very simple thing. It is what remains when everything else has been removed. We use the word for sealed containers, vacuum cleaners, laboratory chambers, and the wide spaces between planets. In everyday speech, it usually means an empty region. In physics, however, emptiness becomes more difficult to define the closer we examine it. A household vacuum cleaner does not create a true vacuum. It merely lowers the air pressure inside part of the machine, allowing the greater pressure of the surrounding atmosphere to push dust and air inward. Even a carefully engineered laboratory chamber is not completely empty. Vacuum pumps can remove an enormous proportion of the gas molecules, but a few particles still remain, moving through the chamber and occasionally colliding with its walls. Atmospheric pressure itself comes from the countless molecules in the air. Nitrogen, oxygen, argon, water vapour, and smaller quantities of other gases move constantly in every direction. As they strike surfaces, they transfer momentum. Each individual impact is unimaginably small, but their combined effect produces the pressure that surrounds us at sea level. When a vacuum pump removes most of those molecules, the number of collisions falls. The pressure becomes lower, and the chamber begins to resemble what we casually call empty space. Yet it has not become nothing. The chamber walls remain. Gravity still passes through it. Light can travel across it. Residual molecules continue to drift around inside, and electromagnetic fields may still be present. The natural vacuum of outer space is similarly incomplete. Interplanetary space contains particles released by the Sun, including the stream of charged matter known as the solar wind. The space between stars contains thin clouds of hydrogen, helium, dust, and energetic particles. In many regions, there may be only around one atom in each cubic centimetre, although the density varies greatly from one environment to another. Between galaxies, matter can be thinner still. Vast cosmic voids contain far less material than galaxies or galaxy clusters, but they are not absolute emptiness. Sparse atoms remain. Photons from the cosmic microwave background travel through them. Neutrinos pass almost unhindered across enormous distances. Gravitational fields extend through them, and dark matter may also be present even where ordinary luminous matter is exceedingly rare. Human beings have argued over the possibility of a true void for thousands of years. Aristotle rejected the idea that empty space could genuinely exist. In his view, nature did not permit a perfect vacuum. Matter would always move to fill any opening, a principle later summarized by the phrase that nature abhors a vacuum. This belief remained influential for centuries, partly because creating a convincing vacuum was technically difficult. Everyday experience seemed to support Aristotle. Water rose in pumps, air rushed into opened containers. Empty spaces did not appear to remain empty for long. During the 17th century, experiments began to change this picture. Evangelista Torricelli filled a long glass tube with mercury and inverted it into a dish of the same liquid. Most of the mercury remained suspended in the tube, but a space formed above it. Torricelli argued that the atmosphere pressing on the mercury in the dish supported the column, while the upper region contained very little matter. Blaise Pascal later tested the connection between atmospheric pressure and altitude. Measurements taken at different heights showed that the mercury column became shorter as the weight of the overlying atmosphere decreased. The behaviour was not caused by some mysterious tendency of nature to prevent emptiness. It followed from the physical pressure of air. Otto von Guericke made the reality of air pressure even more dramatic. He joined two hollow metal hemispheres, removed much of the air from inside them, and demonstrated that teams of horses struggled to pull them apart. The hemispheres were not held together by suction, acting like an invisible glue. They were pressed together by the atmosphere outside. These experiments established that apparently empty regions could be created, measured, and studied. They also showed that air was a physical substance with weight and pressure, rather than an invisible absence. Later, Isaac Newton described space in a very different way from Aristotle. In Newtonian mechanics, space could exist as a fixed background within which matter moved. A region might contain no particles and no light, yet distance, direction, and duration would remain. Objects could later pass through that space, and gravity could still act across it. Classical physics therefore allowed scientists to imagine an ideal vacuum. Remove every atom, every molecule, and every ray of radiation, and what remained would be empty space itself. It would have no material contents, but it would still provide the silent stage on which matter and motion could appear. Quantum physics changes the question. Instead of asking only whether objects are present, it asks what state the underlying physical fields occupy. Modern quantum field theory describes particles as excitations of fields extending throughout space. Electrons belong to an electron field. Photons are excitations of the electromagnetic field. Other particles are associated with other quantum fields. Removing particles does not necessarily remove those fields. The fields remain, even when they occupy their lowest available energy state. This lowest energy condition is what physicists call the quantum vacuum. A quantum vacuum therefore cannot be manufactured simply by attaching a better pump. It is not merely a chamber with fewer molecules. Its exact meaning depends on which fields are being studied, what quantum state they occupy, how an observer is moving, and whether space-time itself is flat, accelerating, expanding, or curved by gravity. Empty space in modern physics is no longer a simple absence. It is a physical state with rules, structure, and measurable consequences. The old question was whether anything remained after matter had been removed. The newer and stranger answer is that the fields of nature were never removed at all. For a long time, physics described the universe mainly in terms of objects. Planets moved through space. Stones fell towards the ground. Tiny particles collided, changed direction, and carried motion from one place to another. Space itself was often treated as little more than the stage on which these objects performed. Fields introduced a different way of thinking. A classical field is a physical quantity that has a value at every point in space, and, in many cases, at every moment in time. A temperature map provides a simple example. Different places in a room can have slightly different temperatures, even though temperature is not a separate object sitting in each location. Together, those values form a temperature field. Gravity can also be described using a field. At every point around Earth, the gravitational field has a particular strength and direction. A falling object responds to the field at its location. It does not need to be physically connected to the planet by a rope, spring, or invisible hand, which is fortunate because the sky would otherwise be rather cluttered. The field concept became especially important during the 19th century through the work of Michael Faraday. Faraday had relatively little formal mathematical education, but he possessed an extraordinary physical intuition. While studying electricity and magnetism, he began to picture space as filled with lines of force. Iron filings scattered near a magnet reveal a familiar pattern. They arrange themselves along curved paths extending between the magnetic poles. Faraday did not regard these lines as merely a convenient drawing. He believed they represented something physically meaningful about the space surrounding the magnet. The magnetic influence was not simply jumping across an empty gap from one object to another. The region between the objects had acquired structure. Every location around the magnet possessed a magnetic strength and direction, and another magnet or moving electric charge would respond according to where it was placed. Faraday developed similar ideas for electric fields. An electric charge altered the space around it, producing an influence that could act upon other charges. The field became the intermediary. Empty space was no longer entirely passive. It could hold a physical condition and carry an influence from one region to another. James Clerk Maxwell transformed Faraday's physical insights into a powerful mathematical theory. During the 1860s, Maxwell brought electricity and magnetism together in a set of relationships now known as Maxwell's equations. These equations describe how electric charges produce electric fields, how electric currents produce magnetic fields, and how changing electric and magnetic fields generate one another. A changing electric field can create a magnetic field. A changing magnetic field can create an electric field. Once produced, the two disturbances can continue travelling together through space as an electromagnetic wave. When Maxwell calculated the speed of these waves, he found that it matched the known speed of light. The conclusion was remarkable. Light itself was an electromagnetic wave. Visible light, radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays are all forms of the same underlying phenomenon. They differ mainly in wavelength and frequency, but all consist of travelling disturbances in the electromagnetic field. This changed the status of apparently empty space. A region containing no ordinary matter could still contain electric and magnetic fields. It could carry light across immense distances. Energy and momentum could travel through it even when no atoms or visible objects were present. The older particle-centered picture had not become useless. Particles remained essential, but fields now shared the stage. Matter could produce fields, fields could guide matter, and fields could propagate independently through regions that looked empty. By the end of the 19th century, classical field theory had become one of the great successes of physics. Yet a collection of puzzling experiments began to suggest that classical ideas were incomplete. One important problem involved black-body radiation. A black body is an idealized object that absorbs all incoming electromagnetic radiation and emits a spectrum determined by its temperature. Classical physics predicted far too much radiation at very high frequencies, leading to what became known as the ultraviolet catastrophe. In 1900, Max Planck found a mathematical solution. He proposed that matter emitted and absorbed electromagnetic energy in discrete amounts, rather than in an entirely continuous flow. The size of each amount depended on the frequency of the radiation. Planck initially treated this quantization cautiously, almost as a mathematical necessity. Nevertheless, it introduced a radical possibility. Energy exchange might occur in distinct packets. Albert Einstein took the idea further in 1905 while explaining the photoelectric effect. When light strikes certain metals, it can release electrons. Increasing the brightness of low-frequency light does not necessarily release electrons, while sufficiently high-frequency light can do so even at low intensity. Einstein proposed that light behaves in interactions as though its energy is concentrated into individual quanta, later called photons. Each photon carries an amount of energy determined by its frequency. One sufficiently energetic photon can free an electron, while many lower energy photons may each be unable to do so. Light now appeared to possess both wave-like and particle-like properties. The calm, continuous electromagnetic wave of Maxwell's theory had acquired a distinctly granular side. Early quantum mechanics focused largely on particles. Erwin Schrödinger described systems using wave functions, mathematical objects that encode the possible outcomes of measurements. Werner Heisenberg developed an alternative formulation using arrays of quantities called matrices. Both approaches successfully described atoms, electrons, and other microscopic systems. Yet difficulties appeared when physicists tried to combine quantum mechanics with Albert Einstein's special theory of relativity. Relativity allows energy to be converted into matter, and matter into energy. High-energy processes can create particles, while particles can disappear through annihilation. A theory that assumes a permanently fixed number of particles cannot describe such events naturally. Paul Dirac made a crucial advance in 1928 by developing a relativistic equation for the electron. Dirac's theory described the electron's quantum behaviour while respecting special relativity, but it also contained unexpected solutions. Those solutions eventually led to the prediction of antimatter. The electron had an antiparticle, now called the positron, with the same mass and opposite electric charge. Carl Anderson experimentally discovered the positron in 1932. The appearance of antiparticles revealed something profound. Quantum mechanics and relativity together seemed to demand a framework in which particles could be created and destroyed. Quantum field theory provided that framework. Instead of treating particles as the most fundamental ingredients in fields as secondary effects surrounding them, it treated the fields themselves as quantum objects. The electromagnetic field became a quantum field. The electron field became a quantum field. Other particle types were associated with their own fields. These fields extend throughout space, and their possible states obey quantum principles. Within this description, a particle is a quantist excitation of a field. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. The particle is not usually imagined as a tiny bead made from field material. It is a particular, detectable quantum state of the field. This picture allows particles to appear and disappear because the field can gain or lose excitations. It also explains why every electron in the universe has exactly the same basic properties. Electrons are not individually manufactured objects that merely happen to resemble one another. They are excitations of the same underlying electron field. The field-based universe is therefore deeper than a collection of particles travelling through emptiness. Even where no particles are detected, the quantum fields remain. Removing every photon does not remove the electromagnetic field. Removing every electron does not erase the electron field. What remains is the lowest energy state those fields are capable of occupying. It may contain no detectable particles, but it is not the absence of the fields themselves. The classical vacuum was imagined as an empty stage waiting for matter and radiation to arrive. The quantum vacuum is closer to the quietest possible state of the stage, the scenery, and the instruments all at once. Nothing obvious may be happening, but the physical framework remains present everywhere. The vacuum state is not the absence of physical reality. It is the lowest energy state that a quantum field can occupy. That distinction is easy to overlook because ordinary language encourages us to imagine emptiness as nothing at all. Remove the particles, remove the light, remove the heat, and surely there should be nothing left. Quantum field theory gives a different answer. The fields remain, and even in their quietest possible condition, they cannot always be assigned perfectly still and exact values. A useful way to understand this begins with one of the simplest systems in physics, the harmonic oscillator. A harmonic oscillator is anything that tends to return towards an equilibrium position when displaced. A mass attached to a spring is the familiar example. Pull the mass away from its resting point and release it, and the spring draws it back. The mass passes through the centre, continues to the other side, and oscillates backwards and forwards. In classical physics, there is no mystery about the oscillator's lowest energy state. The mass can sit exactly at the equilibrium position with no motion at all. Its position is perfectly defined, its momentum is exactly zero, and its total energy can be reduced to zero. Quantum mechanics does not permit quite the same arrangement. Werner Heisenberg's uncertainty principle states that certain pairs of physical quantities cannot both possess arbitrarily precise values in the same quantum state. The best-known pair is position and momentum. The more precisely a system's position is defined, the less precisely its momentum can be defined, and the reverse is also true. This is not simply the result of poor instruments or clumsy measurement. It is a property of the quantum state itself. Nature does not quietly keep both values perfectly fixed while waiting for someone to build a better machine. Suppose a quantum oscillator were placed exactly at its equilibrium point with exactly zero momentum. Its position and momentum would then both be perfectly known. That would violate the uncertainty principle. The lowest energy quantum state must therefore retain some unavoidable spread. The oscillator cannot be compressed into a condition of perfect stillness and perfect localization. Even in its ground state, which is the lowest energy it is allowed to have, its position and momentum remain described by probability distributions. This residual ground state energy is called zero-point energy. The name can sound slightly contradictory. Zero-point energy is not zero energy. It is the energy present at the lowest point available to the quantum system. There is simply no permitted state beneath it. The oscillator is sometimes described as continuing to move even at absolute zero, but that phrase needs care. Zero-point motion does not mean a tiny object follows a hidden path, wobbling steadily from side to side like a miniature clockwork toy. In the ground state, the system does not have a definite classical trajectory. Instead, its quantum state contains an unavoidable range of possible outcomes for position and momentum. Repeated measurements on identically prepared oscillators would not always produce exactly the same values. The non-zero energy belongs to this quantum state and its structure, not to a secretly bouncing object whose route is merely concealed from view. Quantum fields inherit this same basic behaviour. A field can be broken down mathematically into different wave modes. A guitar string offers a loose comparison. It can vibrate in a fundamental mode, in higher harmonics, and in combinations of many patterns. A field extending through space can also support many possible wavelengths and frequencies. Each individual mode of a quantum field behaves mathematically much like a quantum harmonic oscillator. It can occupy different energy levels, with higher levels corresponding to greater excitation. In a quantized field, those excitations are associated with particles. For the electromagnetic field, one quantum of excitation is a photon. A mode containing more photons occupies a higher energy state. When no photons are present, the mode rests in its ground state. Yet that ground state still has zero-point energy. The quantum vacuum is formed when every mode of the field occupies its lowest permitted state. There may be no detectable particles, but the field has not been erased. Each mode retains the ground state properties required by quantum mechanics. A classical field can in principle be perfectly calm. Its value could be fixed exactly at every point, with no motion and no uncertainty. If the classical electromagnetic field was zero everywhere, then every location would simply contain an exact value of zero. A quantum field is described differently. Even when its average value is zero, individual measurements need not always return zero. The vacuum state can contain a distribution of possible field values, with fluctuations around the average. This does not mean that the field is randomly changing in exactly the same way as a classical signal being disturbed by noise. The uncertainty belongs to the quantum description. different measurements probe different aspects of the state, and the outcomes follow precise statistical rules. The vacuum is therefore quiet without being featureless. It has no ordinary particles, yet it still possesses correlations, uncertainties, and ground state properties. The phrase lowest energy also requires some caution. In many areas of non-gravitational physics, only differences in energy directly affect measurable outcomes. The zero of energy can sometimes be shifted without changing the predictions. A physicist may choose a convenient reference point and describe the vacuum energy as zero relative to that choice. Gravity makes the issue more complicated. According to Albert Einstein's general theory of relativity, energy and pressure influence the curvature of space-time. If vacuum energy gravitates, its absolute value may have physical consequences for the expansion and geometry of the universe. This is one reason vacuum energy becomes such a deep problem. Quantum field theory naturally associates ground state energy with every field mode, while gravity appears to respond to energy itself. Bringing those two ideas together remains one of the great unfinished tasks in fundamental physics. There is also no single vacuum state that can be described without mentioning the fields involved. The electromagnetic field has a vacuum state. The electron field has a vacuum state. The quark and gluon fields of quantum chromodynamics have their own ground state structure. The Higgs field has a non-zero value, even in what physicists call the vacuum. Interactions between fields can alter the nature of the lowest energy state. The vacuum of a collection of non-interacting fields is simpler than the vacuum of fields that influence one another. In the real universe, the fields of the Standard Model are not isolated, and their shared ground state can possess a rich internal structure. The existence of zero-point energy does not mean that limitless usable power can be drawn from empty space. A ground state is already the lowest state available. There is nowhere lower for the system to fall while releasing a convenient supply of energy. Useful energy requires a difference between states. A battery works because chemical energy can move from a higher energy arrangement to a lower energy one. Water can drive a turbine because it descends from a higher position to a lower one. A system already resting in its true ground state offers no lower destination from which an endless stream of work could be obtained. The quantum vacuum can still produce measurable effects when fields interact with matter, boundaries, acceleration, or curved spacetime. Those effects do not come from casually opening a valve into an infinite cosmic fuel tank. They arise from differences between physical configurations and from energy supplied or redistributed through real interactions. The vacuum state is therefore not nothingness, and it is not a hidden battery. It is the quietest condition nature allows a quantum field to possess. Even there, at the lowest possible energy, perfect stillness remains out of reach. The phrase vacuum fluctuation is often used as though it describes a restless cloud of tiny particles appearing from nowhere, surviving for a moment, and then vanishing before nature notices. It is a memorable image. It is also easy to take far too literally. In quantum field theory, a vacuum fluctuation refers more precisely to the non-zero variation found in measurements of a quantum field when that field is in its vacuum state. The average value of the field may be zero, while the possible outcomes of individual measurements still possess a spread. A simple comparison is a balanced distribution of numbers. Suppose the values are arranged equally above and below zero. Their average can be exactly zero even though most of the individual values are not. Zero average does not mean no variation. The same basic idea appears in the quantum vacuum. A field can have an average value of zero, while still possessing uncertainty, correlations, and a range of possible measurement results. These are not arbitrary disturbances added from outside. They are properties of the vacuum state itself. Correlation functions provide one of the main mathematical ways of describing this structure. They express how the outcome of a field measurement at one place and time is related statistically to a measurement elsewhere. Even in the vacuum, these relationships do not generally disappear. The state has organisation, even when it contains no ordinary detectable particles. Popular explanations often translate this mathematics into the statement that virtual particles constantly pop into existence and disappear again. This picture can sometimes help create an initial intuition, but it should not be mistaken for a literal film of what is happening inside empty space. Virtual particles are mathematical features that arise in certain methods of calculation, particularly perturbation theory. Perturbation theory begins with a simpler system and then adds the effects of interactions in a controlled sequence of corrections. Feynman diagrams provide a visual way of organising those corrections. They were developed through the work of Richard Feynman and are closely connected to the independent advances made by Julian Schwinger and Shinichiro Tominaga. Together, these physicists helped establish the modern form of quantum electrodynamics, the quantum field theory of light and electrically charged particles. In a Feynman diagram, the external lines usually correspond to particles prepared or detected in an experiment. Internal lines represent mathematical contributions within the calculation. These internal contributions are often called virtual particles. A virtual particle is not an ordinary particle, briefly hiding from the detector. It does not need to satisfy the same relationship between energy, momentum, and mass as a real detectable particle. That is possible because it is not a directly observed object. It is part of the mathematical procedure used to calculate the probability of an observable outcome. Different calculation methods can describe the same physical process without presenting exactly the same collection of virtual particles. This is another reason they should not be treated as literal miniature objects following hidden paths through space. The uncertainty principle is also frequently misused here. It is sometimes claimed that the universe can borrow energy for a short time, provided that it pays the energy back quickly enough. This is not a reliable statement of quantum physics. Energy conservation is not casually suspended during quantum events. In a system whose laws do not change with time, conservation of energy remains built into the theory. The energy-time uncertainty relation concerns limits involving the duration and energy width of processes or states. It is not a permission slip allowing nature to create arbitrary energy from nothing. Real particles can certainly be produced, but a physical source of energy must be involved. A sufficiently energetic collision can convert kinetic energy into new particles. An intense electric field can supply energy for the creation of an electron and a positron. A rapidly changing boundary can transfer energy into photons. Expanding or curved space-time can change the way quantum fields are divided into vacuum and particle states. In every case, the energy comes from the collision, the field, the moving boundary, the gravitational setting, or another identifiable physical source. The vacuum does not quietly cover the bill and hope no one checks the receipt. None of this makes the quantum vacuum inert. Vacuum correlations contribute to real physical predictions. They appear in calculations involving atomic energy levels, electromagnetic interactions, forces between closely spaced surfaces, and the behaviour of quantum detectors. The important distinction is between three different layers of description. There is intuitive language, which helps create a mental picture. There is the mathematical formalism, which produces precise predictions. And there are experimental outcomes, which determine whether those predictions agree with nature. Problems arise when the intuitive picture is treated as though it were the formal theory itself. Saying that particles pop in and out of existence can be a convenient shortcut, but it can also suggest a tiny, invisible storm that quantum field theory does not require. The vacuum is remarkable for a subtler reason. It is a highly organized quantum state with measurable correlations and definite physical properties. Its average fields may vanish, yet its quantum structure remains. Replacing the myth with a more careful explanation does not drain the mystery from empty space. It reveals something more interesting than a swarm of temporary particles. The quietest state in nature still contains relationships, probabilities, and a structure precise enough to leave traces in the measurable world. an atom may appear to be a small and self-contained piece of matter, quietly carrying its electrons and nucleus through space. In quantum physics, however, no atom is completely isolated. Even when no ordinary light is present, the charged particles inside the atom remain coupled to the electromagnetic field surrounding them. The electromagnetic field does not disappear when a room becomes dark or when every detectable photon has been removed. It remains in its vacuum state, the lowest energy condition permitted by quantum theory. An atom placed in this vacuum is therefore not sitting in absolute nothingness. Its electrons continue to interact with a quantist field whose ground state has structure, uncertainty, and measurable consequences. One of the clearest examples appears when an atom is excited. An electron in an atom can occupy only certain allowed energy states. If energy is supplied, perhaps through a collision or by absorbing light, the atom can be lifted into a higher energy state. It does not usually remain there forever. After some characteristic amount of time, the atom returns to a lower energy state and releases the difference in energy as a photon. This process is called spontaneous emission. The word spontaneous can make the event sound as though it has no physical cause. More precisely, the excited atom is coupled to the quantized electromagnetic field. The combined system of atom and field evolves from a state containing an excited atom, a no-emitted photon, into a state containing a lower energy atom and a photon travelling away. Classical electromagnetism alone cannot provide a complete description of this event. A classical atom placed in a perfectly empty electromagnetic field would not necessarily have a mechanism that produces the observed spontaneous transition in the same way. Quantizing the field allows the atom to exchange energy with it even when the field begins in its vacuum state. It is often said that vacuum fluctuations stimulate the atom to emit. This can be a useful description, but it is not the only valid way to divide the physics. The same process can also be discussed through the atom's own interaction with the electromagnetic field and its radiation reaction. What matters experimentally is that the quantized atom and quantized field together predict spontaneous emission accurately. The influence of the electromagnetic vacuum can be detected even more delicately in the energy levels of hydrogen. Hydrogen is the simplest atom, containing a single proton and a single electron. Paul Dirac's relativistic theory of the electron provided an extraordinarily successful account of its structure. According to the simplest Dirac prediction, two particular hydrogen states should have exactly the same energy. In 1947, Willis Lamb and Robert Rutherford carried out a precise experiment using microwave techniques. They discovered that the two states were not perfectly aligned. One sat at a slightly different energy from the other. The difference became known as the Lamb shift. The size of the shift is tiny compared with the total energy binding the electron to the proton. Its best-known contribution in hydrogen corresponds to a frequency of roughly 1000 MHz. Yet that small discrepancy was large enough to reveal that the atom could not be understood as an electron moving in a static electric field alone. Quantum electrodynamics explained the effect by treating both charged particles and the electromagnetic field quantum mechanically. The electron continually interacts with the field around it. Calculations must include quantum corrections associated with the electron's self-energy, vacuum polarization, relativistic behaviour, and the finite properties of the proton. The language of an electron interacting with its own field can sound peculiar, but it does not mean the electron is simply pushing itself around in the classical sense. Quantum electrodynamics calculates how the observable electron differs from an idealized bare particle once its interactions with the surrounding quantum fields are included. These corrections slightly alter the allowed atomic energy levels. The Lamb shift therefore provides direct evidence that the electromagnetic vacuum and quantum interactions affect the structure of matter. Vacuum polarization is another part of this story. In quantum electrodynamics, the presence of an electric charge influences the charged quantum fields around it. These fields modify the way the electromagnetic interaction is transmitted through space. A common analogy describes the quantum vacuum as partially screening an electric charge. From a greater distance, the observed charge appears slightly different from the effective charge measured at a much shorter distance. The analogy is useful, provided it is not interpreted as a literal cloud of ordinary particles permanently surrounding the electron. More precisely, quantum processes involving charged fields modify the propagation of the electromagnetic interaction. As a result, the effective strength of the electric charge depends slightly on the energy or distance scale at which it is examined. At very short distances, or equivalently at high energies, the electromagnetic interaction appears a little stronger. This scale dependence is known as the running of the electromagnetic coupling. It is small at familiar energies, but modern experiments can measure it. An even more precise test comes from the magnetic behaviour of the electron. A moving electric charge behaves magnetically, and the electron possesses an intrinsic form of angular momentum called spin. Together, these properties give the electron a magnetic moment, making it behave in some respects like an extremely small magnet. Paul Dirac's original theory predicted a particular value for this magnetic moment. Quantum electrodynamics adds a small correction called the anomalous magnetic moment. That correction arises from the electron's interaction with quantum fields, including contributions represented in calculations through increasingly elaborate Feynman diagrams. The experimental and theoretical values agree to an astonishing degree. Measurements of the electron's magnetic moment have reached precision at the level of parts in a trillion, while quantum electrodynamics calculations include contributions from many orders of increasingly subtle corrections. This agreement is among the most precise confirmations of any physical theory. It does not prove that every future extension of quantum field theory has already been discovered, but it shows that the theory's description of electrons, photons, and vacuum-related quantum effects is remarkably accurate. Experiments of this kind depend on extraordinary control. Researchers trap individual electrons, cool atomic systems, measure transition frequencies, and compare clocks whose rates can be affected by unimaginably small changes in energy. The National Institute of Standards and Technology in the United States is one of the organizations involved in precision spectroscopy, atomic clocks, and measurements of fundamental constants. Similar work is carried out at institutions including the National Physical Laboratory in the United Kingdom, the National Metrology Institute of Germany, and specialist university laboratories around the world. Modern optical atomic clocks compare frequencies so precisely that they can detect the gravitational effect of changing height by a surprisingly small amount. High-resolution spectroscopy can resolve shifts in atomic energy that would be completely invisible in ordinary conditions. These instruments turn tiny quantum corrections into measurable frequencies. The Lamb shift, spontaneous emission, vacuum polarization, and the electron's magnetic moment are all extremely subtle. None would be noticed by watching an atom with the naked eye, even with a very determined expression, yet together they reveal something important. The vacuum is not merely an abstract idea placed behind the equations. Its quantum structure affects how atoms release light, how electrons respond to fields, how electric charge appears at different scales, and where atomic energy levels are found. Empty space does not overwhelm matter with dramatic activity. Its influence is quieter than that. It appears as tiny shifts, faint corrections, and precise deviations from simpler predictions. Those deviations can be measured, and through them, the supposedly empty background becomes part of the observable physics of light and matter. Two pieces of metal can attract one another without carrying any net electric charge, without being magnetic, and without anything obvious passing between them. The effect is extraordinarily small, unless the metals are brought almost impossibly close together. Yet when the separation shrinks to the scale of nanometers or micrometers, the force becomes measurable. This is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir considered two flat parallel conducting plates placed close together in a vacuum. Both plates were electrically neutral. Classical physics offered no obvious reason for them to attract. Casimir predicted that quantum electrodynamics would produce a small force drawing the plates towards one another. The origin of that force lies in the relationship between quantum fields and boundaries. The electromagnetic field can support many different wave modes. A mode is a particular pattern of oscillation with a particular wavelength, frequency, and spatial form. In open space, an enormous range of modes is possible. Between two conducting plates, however, the field must obey specific boundary conditions. Electric charges inside a conductor can move in response to an electromagnetic field. As a result, the electric field at the conducting surfaces must satisfy strict conditions. Only certain standing wave patterns fit between the plates in the permitted way. A loose comparison can be made with a string fixed at both ends. The string cannot vibrate with just any wavelength. Only patterns that fit neatly between the fixed points are allowed. The electromagnetic field between the plates is far more complicated, but the general idea is similar. Outside the plates there is much more room, so a broader set of field modes is available. Between them, the permitted modes are restricted by the narrow separation and the conducting surfaces. In one common description, this difference changes the total zero-point energy of the electromagnetic field. The vacuum state between the plates has a slightly different energy from the vacuum state outside them. The plates are pushed towards the arrangement with lower energy, producing an attractive force. The same effect can also be described in terms of vacuum stress. The electromagnetic field carries momentum and exerts pressure. The allowed quantum field structure differs inside and outside the gap, creating a small imbalance of stress across the plates. There are also equivalent approaches that focus on the fluctuating charges and currents within the conducting materials and their interactions through the electromagnetic field. These descriptions do not represent separate competing forces. They are different ways of organizing the same underlying physics. This is an important point because the Casimir effect is sometimes presented as direct proof that an infinite quantity of vacuum energy is physically waiting inside empty space. What experiments actually measure is a difference between two configurations. The force depends on how the field and materials behave when the plates are at one separation compared with another. It does not require an independently measurable ocean of absolute vacuum energy. In quantum field theory, differences in energy and stress are often far more directly meaningful than assigning a separate observable value to every contribution in isolation. For ideal, perfectly conducting parallel plates, the attractive pressure increases extremely rapidly as the separation becomes smaller. It varies inversely with the fourth power of the distance. Halving the gap therefore makes the ideal pressure 16 times greater. At a separation of around 1 micrometer, the pressure is still only about 1,000th of a pascal. That is very small compared with ordinary atmospheric pressure. At around 100 nanometers, however, the ideal pressure rises to roughly 10 pascals. Across a sufficiently large surface, that becomes much easier to detect. Real experiments are more difficult than the ideal calculation suggests. Perfectly parallel plates must be aligned with extraordinary precision. Surfaces have roughness. Metals are not perfect conductors. Residual electric potentials, temperature, contamination, and mechanical vibration can all imitate or modify the force. For this reason, many measurements use a metal-coated sphere placed close to a flat plate, rather than two perfectly parallel surfaces. The curved geometry is easier to control, though it requires additional modelling. One of the most influential measurements was reported by Steve Lamoureux in the 1990s. His experiment used a torsion pendulum to detect the tiny force between conducting surfaces. The result broadly agreed with Casimir's prediction and helped establish the effect as an experimentally accessible phenomenon. Later research groups improved the measurements using atomic force microscopes, microfabricated oscillators, and carefully prepared metallic coatings. Modern experiments compare results with detailed theoretical models that include conductivity, geometry, temperature, and surface properties. A related interaction had been predicted by Hendrik Casimir and Dirk Polder. The Casimir polar force acts between a neutral atom and a nearby surface, or more generally between polarizable neutral objects. An atom with no net electric charge can still develop a temporary electric dipole because its electron cloud is a quantum system. The distribution of charge is not perfectly rigid. Field fluctuations and atomic fluctuations become correlated with the response of the nearby surface, producing an attractive interaction. At shorter distances, this behaviour connects with the van der Waals force between neutral atoms and molecules. At greater distances, the finite travel time of electromagnetic interactions becomes important, producing the Casimir polar form of the force. These effects matter well beyond carefully arranged physics experiments. In nanotechnology, engineers build devices with components separated by distances comparable to the range over which Casimir forces become significant. Micro-electromechanical systems and nano-electromechanical systems contain tiny switches, sensors, mirrors, resonators, and moving surfaces. At ordinary human scales, gravity, friction, and mechanical stiffness dominate. At microscopic scales, surface forces become proportionally much more important. Two small components can attract and stick together in a failure known as stiction. Casimir forces are not always the only cause, since electrostatic effects, moisture, and chemical adhesion can also contribute. Nevertheless, quantum and electromagnetic surface interactions must be considered when machines become small enough. Researchers can also modify Casimir forces by changing the materials, geometry, temperature, or intervening medium. Under carefully chosen conditions, related configurations may produce reduced attraction or even effective repulsive behaviour. This is not anti-gravity, but it can be useful when designing microscopic systems that need to avoid sticking. The ordinary Casimir effect is static. The boundaries remain in place, and the measurable result is a force associated with the allowed field configurations. The dynamical Casimir effect is different. If a boundary condition changes rapidly enough, the quantum field may be driven out of its vacuum state. Energy supplied by that changing boundary can then appear as real photons. Moving a physical mirror fast enough is extremely difficult, so experiments often imitate rapid boundary motion using superconducting circuits. By changing the electrical properties of a circuit at very high speed, researchers can alter the effective boundary experienced by microwave fields. Radiation consistent with dynamical Casimir photon production has been observed in such systems. The photons do not emerge without an energy source. The energy comes from the external equipment driving the changing boundary. Once again, the vacuum is not quietly offering a complementary supply of electricity. The Casimir effect reveals something subtler. Quantum fields respond to the shape, material, and separation of physical boundaries. Change the available field configurations, and a measurable force can appear. Two silent plates in an almost empty chamber can therefore reveal that empty space is not merely a passive gap. Even in its lowest energy state, the electromagnetic field retains enough structure for geometry to matter. Quantum field theory contains an awkward mathematical surprise. Every possible mode of a quantum field behaves like a quantum oscillator, and every oscillator has a lowest permitted energy. When all of those zero-point energies are added together, the total appears to become infinite. The reason is not that any single mode has infinite energy. Each individual contribution is finite. The difficulty comes from the number of modes available. A field can support waves with many different wavelengths. Long waves contribute, short waves contribute, even shorter waves contribute as well. In the simplest continuous description, there is no final shortest wavelength, so the number of possible modes continues without limit. Higher frequency modes possess greater zero-point energy. Adding infinitely many increasingly energetic contributions produces a sum that diverges. Instead of arriving at a very large but manageable value, the calculation runs away towards infinity. This is clearly a problem if the result is interpreted as a directly measurable amount of energy filling every region of space. Nature does not appear to place infinite energy inside an empty laboratory chamber. The universe has also shown a commendable ability to avoid instantly collapsing beneath an infinite gravitational burden. Vacuum energy was not the only place where infinities appeared. Similar difficulties emerged during the early development of quantum electrodynamics. An electron has an electric charge and therefore interacts with the electromagnetic field. In classical theory, the field around a point-like charge becomes increasingly strong as the distance from the charge approaches zero. Trying to calculate the energy stored in that field produces an infinite result. Quantum theory added further corrections. An electron interacts with the quantized electromagnetic field, and early calculations of its self-energy appear to shift its mass by an infinite amount. Corrections to electric charge and other measurable properties also produce divergent expressions. The theory was making excellent qualitative predictions, but some of its calculations seemed determined to fill the page with infinities before quietly refusing to continue. A practical breakthrough came in 1947, after Willis Lamb and Robert Rutherford measured the Lamb shift in hydrogen. Hans Bethe showed that a carefully organised calculation could produce a finite approximate value for the observed shift. His result helped demonstrate that the divergent terms could be handled without abandoning quantum electrodynamics. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga then developed systematic methods for calculating quantum electromagnetic interactions. Their approaches looked different on the surface. Feynman used the diagrammatic method now associated with Feynman diagrams, while Schwinger and Tominaga developed more formal operator-based techniques. Freeman-Dyson later showed that these approaches were mathematically equivalent and helped organize them into a unified framework. The central procedure became known as renormalization. Renormalization begins by recognizing that some quantities appearing in the original equations are not themselves directly observable. A theory may contain an initial mass parameter and an initial electric charge parameter, sometimes informally called bare quantities. Once quantum interactions are included, those parameters receive corrections. The experimentally observed electron mass is therefore treated as the combined result of the original parameter and all relevant interaction effects. The same principle applies to the measured electric charge and the strength of other interactions. Instead of attempting to assign separate physical meaning to an infinite bare mass and an infinite correction, physicists express the theory in terms of finite quantities that experiments actually measure. This is not simply a matter of spotting an infinity and crossing it out. Renormalization is a structured mathematical relationship between parameters defined at one energy scale and measurable quantities defined at another. A useful first step is regularization. A calculation is temporarily modified so that divergent expressions become controlled. One method imposes a maximum energy or minimum wavelength, known as a cutoff. Another changes the number of dimensions used in the mathematics through dimensional regularization. The regulated calculation exposes exactly where the troublesome terms occur. The parameters of the theory are then redefined so that the final predictions for measurable quantities remain finite and consistent. Once the process is complete, the temporary regulator can be removed. A successful renormalizable theory leaves behind finite predictions that do not depend on the arbitrary device used to control the intermediate infinities. Quantum electrodynamics is spectacularly successful in this respect. Renormalized calculations predict the electron's magnetic moment, atomic energy shifts, scattering probabilities, and many other quantities with extraordinary accuracy. The modern interpretation of renormalization is closely connected to the idea of an effective field theory. An effective field theory is designed to describe physics accurately across a particular range of energies or distances. It does not necessarily claim to remain complete at every imaginable scale. The physics of ocean waves can be described without tracking every molecule of water. The behaviour of solids can be calculated without first solving every detail of quarks and gluons. In the same way, A quantum field theory can provide precise low-energy predictions even if a deeper theory becomes necessary at far higher energies. Effects associated with unknown high-energy physics are organized into additional terms whose influence is usually suppressed at lower energies. This allows physicists to calculate reliably within the domain where the theory has been tested. From this perspective, renormalization explains how the description of physical parameters changes with scale. The effective electric charge, for example, depends slightly on the distance or energy at which it is measured. Rather than being an embarrassment, this running of the coupling is now a central and experimentally verified feature of quantum field theory. Vacuum energy seems easier to manage when gravity is absent. In ordinary, non-gravitational quantum field calculations, it is usually energy differences that determine observable behaviour. If the same constant amount is added to the energy of every possible state, transition frequencies and scattering probabilities remain unchanged. The entire energy scale has simply been shifted together. A convenient reference can therefore be chosen in which the vacuum energy is defined as zero. This resembles measuring height. A mountain can be described relative to sea level, the valley floor or the centre of Earth. Many physical predictions depend on differences in height rather than the chosen location of zero. General relativity changes the situation. Albert Einstein's theory describes gravity as the curvature of space-time produced by energy and momentum. Energy density matters, but pressure also contributes. A constant energy spread throughout empty space cannot necessarily be removed by redefining the reference level, because it may affect the geometry and expansion of the universe. A uniform vacuum energy behaves gravitationally in a distinctive way. It can act like a cosmological constant, contributing negative pressure and driving accelerated cosmic expansion. The mathematical freedom to shift every energy by the same constant in non-gravitational physics therefore becomes physically significant once gravity is included. The chosen zero of energy may alter space-time itself. This leaves two enormously successful theories facing one another across a deep conceptual gap. Quantum field theory naturally produces vacuum contributions and handles many of them through renormalization. General relativity appears to respond to the resulting energy as a source of curvature. Observations indicate that empty space may possess a very small positive energy density associated with the accelerated expansion of the universe. Straightforward quantum field estimates, however, often produce values that are vastly larger. Renormalization successfully turns many quantum infinities into precise predictions. Yet when vacuum energy meets gravity, the problem does not simply disappear. The infinity can be organized. The measurable parameters can be defined. But the remaining value appears to demand an explanation that physics has not yet fully found. Quantum electrodynamics describes the interactions between electrically charged particles and the electromagnetic field. Its vacuum is not the absence of those fields, but their lowest energy shared state. The electron field remains present throughout space. The positron is not described by a completely separate field, but as the antiparticle excitation associated with the same underlying relativistic electron field. Alongside it sits the electromagnetic field, whose detectable excitations are photons. In the quantum electrodynamic vacuum, there are no ordinary electrons, positrons, or photons available for a detector to collect. Even so, the fields continue to exist and interact according to the laws of quantum theory. This means that a real electron is never entirely detached from its surroundings. The simple image of an electron as a bare point carrying a fixed electric charge is useful as a starting point, but it is not the full measurable object. An electron interacts continuously with the electromagnetic field. When physicists calculate its mass, electric charge, magnetic moment, or behaviour during a collision, they must include quantum corrections produced by these interactions. The observed electron is therefore sometimes described as a dressed particle. This does not mean it wears a literal coat of smaller particles. It means that its measurable properties already include the effects of its coupling to the surrounding quantum fields. Quantum electrodynamics calculates these effects using a method called perturbation theory. A complicated interaction is divided into a sequence of contributions, beginning with the simplest approximation and adding progressively smaller corrections. Feynman diagrams provide an organized visual language for keeping track of those terms. Richard Feynman introduced the diagrams as part of his formulation of quantum electrodynamics, building upon the wider theoretical advances made by Julian Schwinger, Shinichiro Tomonaga, and others. A typical diagram uses external lines to represent the particles entering and leaving an interaction. Internal lines represent mathematical contributions that appear during the calculation. The points where lines meet correspond to interactions between the electron field and the electromagnetic field. These diagrams should not be interpreted as photographs of hidden events. The lines do not reveal tiny particles following definite routes that instruments simply fail to see. They are bookkeeping tools used to calculate probability amplitudes. Several different diagrams may contribute to the same observable result. Their mathematical effects must be combined, including quantum interference between the alternatives. Nature does not necessarily select one diagram and then perform it behind the scenes. One important correction is vacuum polarization. Suppose two charged particles interact electromagnetically. In the simplest picture, the electromagnetic field carries that influence between them. Quantum electrodynamics predicts that charged quantum fields modify the propagation of the interaction. This modification is called vacuum polarization. It changes the effective electromagnetic response of the vacuum in the presence of a charge. The effect is sometimes described by imagining the charge surrounded by a screening cloud. The comparison can be helpful, although the cloud should not be mistaken for a collection of ordinary positrons and electrons sitting at fixed locations. More precisely, the interaction between the electromagnetic field and the charged electron field alters the mathematical relationship between the original charge and the charge inferred by measurements performed at different scales. From relatively far away, the surrounding quantum response partially reduces the effective strength that is observed. When the charge is examined at shorter distances, the measurement penetrates further into this response, and the electromagnetic interaction appears slightly stronger. The strength of electromagnetism is commonly expressed through the fine structure constant. At familiar low energies, its value is close to 1 divided by 137. The name constant can sound final, but the effective value changes slightly with energy. This behaviour is called a running coupling. A running coupling does not mean that the laws of physics drift unpredictably from day to day. It means that the effective interaction strength depends in a precise and calculable way on the energy or distance scale used to probe it. High-energy collisions examine much shorter distances than ordinary atomic experiments. Under those conditions, the effective electromagnetic coupling is larger than its familiar low-energy value. Experiments have confirmed this scale dependence. The idea is central to modern quantum field theory. Electric charge is not merely a number stamped permanently onto a particle without context. Its measurable expression is influenced by the quantum fields through which the interaction is transmitted. The quantum electrodynamic vacuum also allows photons to influence one another indirectly. In classical electromagnetism, two beams of light can pass through one another without scattering. Maxwell's equations are linear in empty space, so one electromagnetic wave does not ordinarily deflect another. Photons also carry no electric charge. There is therefore no simple direct photon-to-photon interaction in quantum electrodynamics. Yet photons do interact with the charged electron field. Through that connection, one photon can influence another. This process is called light-by-light scattering. In perturbative calculations, it can be represented by diagrams in which photons couple indirectly through charged field contributions. The internal structure of the calculation is often drawn as a loop connected to 4 photon lines. Again, The loop is not a literal circular track travelled by a sequence of hidden particles. It is a mathematical contribution to the probability that incoming photons will emerge with changed directions or energies. At ordinary light intensities, light-by-light scattering is fantastically weak. 2 torch beams crossing in a dark room will continue on their way with no noticeable disturbance, which is probably for the best. Lighting a hallway would become unnecessarily complicated otherwise. The effect becomes more accessible in extremely strong electromagnetic environments. When heavy atomic nuclei pass close to one another at very high speed, their electric fields can be treated as intense sources of photons. The ATLAS collaboration and the compact muon solenoid collaboration at the European Organisation for Nuclear Research have studied light-by-light scattering and collisions involving heavy ions at the Large Hadron Collider. The measurements found events consistent with photons scattering from photons through the quantum processes predicted by quantum electrodynamics. These observations provided a striking demonstration that electrically neutral light can interact indirectly through charged quantum fields. Quantum electrodynamics therefore gives empty space a very specific kind of activity. The vacuum is not a material substance that establishes a preferred state of rest. It does not behave like the old luminiferous ether once proposed as the medium carrying light. The theory preserves Lorentz invariance, meaning its laws take the same form for all inertial observers. There is no universal experiment that reveals absolute motion through the quantum vacuum. This is essential for compatibility with Albert Einstein's special theory of relativity. Quantum fields fill space, yet they do not turn space into an ordinary mechanical medium with a detectable cosmic wind. The vacuum is active in a more subtle sense. It permits correlations, modifies interactions, contributes quantum corrections, and helps determine how measurable quantities depend on scale. An electron carries the imprint of its field interactions. Electric charge runs with energy. Photons can scatter from one another through charged fields. Each effect follows precise mathematical rules and can be tested against experiment. Supposedly empty space is therefore not an invisible substance and not a swarm of hidden objects. It is the lowest energy state of interacting quantum fields, quiet enough to contain no ordinary particles, yet structured enough to shape how particles and light behave. The electromagnetic vacuum is only one part of the story. Another, far more strongly interacting set of fields shapes the particles found inside every atomic nucleus. The theory describing these fields is called quantum chromodynamics. It is the quantum field theory of quarks, gluons, and the strong interaction. Quarks are the fundamental particles found inside protons, neutrons, and many other short-lived particles. Gluons are the quanta of the fields that carry the strong interaction between quarks. The property that allows quarks and gluons to participate in this force is known as colour charge. Despite the name, it has nothing to do with visible colour. The terms red, green, and blue are simply labels used to distinguish 3 forms of strong charge. Ordinary matter is colour neutral overall. A proton contains 3 quarks, whose colour charges combine into a neutral state. A neutron is organised in the same way. Other combinations, such as a quark paired with an antiquark, can also produce colour-neutral particles. The theory was developed from ideas introduced during the 1960s. Murray Gell-Mann and George Zweig independently proposed that protons, neutrons, and many related particles were composed of smaller constituents now called quarks. Quantum chromodynamics later emerged as the theory governing their interactions. David Gross, Frank Wilczek, and David Politzer discovered a key property known as asymptotic freedom. Asymptotic freedom means that quarks interact more weakly when they are extremely close together or probed at very high energies. At greater separations and lower energies, the strong interaction becomes much more powerful. This is almost the reverse of familiar electromagnetic behaviour. Quarks can move with a degree of freedom over very short distances inside a proton, but trying to pull them far apart strengthens the field between them. Eventually, enough energy is stored in that field to create new quark and antiquark combinations. Instead of extracting a lone quark, the process produces new color-neutral particles. This behavior is known as confinement. The vacuum of quantum chromodynamics is therefore not a passive background in which every field simply rests at zero. The quark and gluon fields interact strongly even in their lowest energy state. Physicists describe some aspects of this structure through quantities known as condensates. A quark condensate reflects the organized ground state behavior of quark and antiquark fields. A gluon condensate describes contributions associated with the gluon fields. These condensates should not be pictured as ordinary droplets of matter floating through empty space. They are properties assigned to the quantum chromodynamic vacuum and help characterize its lowest energy structure. One particularly important effect is spontaneous chiral symmetry breaking. At high energies, the equations describing very light quarks possess an approximate symmetry connected with their left-handed and right-handed quantum behavior. The lowest energy state does not fully preserve that symmetry. The symmetry of the underlying equations remains, but the vacuum settles into a state that does not display it in the same way. This is what physicists mean by spontaneous symmetry breaking. A simple comparison is a perfectly balanced pencil standing on its point. The situation is symmetric in every horizontal direction, but when the pencil falls, it chooses one direction. The laws did not favour that direction in advance, yet the final state does not preserve the original symmetry. In quantum chromodynamics, spontaneous chiral symmetry breaking helps explain the behaviour and relatively low masses of particles called pions. It also influences the internal structure of hadrons, the family of particles that includes protons and neutrons. The structured vacuum contributes indirectly to one of the most familiar facts in the universe. Ordinary matter has mass. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. The bare masses of these constituent quarks account for only a small fraction of the total mass of either particle. Most of the mass comes from the energy of the strong interaction. Quarks move relativistically inside hadrons. Gluon fields carry energy. Quark and gluon interactions continually reshape the internal quantum state. According to the relationship between mass and energy expressed by Albert Einstein, this confined energy contributes to the mass of the proton and neutron. The proton has a mass of roughly 938 million electron volts when expressed in particle physics energy units. The combined bare masses of its 3 main quarks contribute only a small portion of that total. The rest arises mainly from strong field energy and quantum dynamics. This means that much of the mass in the human body does not come directly from the Higgs field acting on quarks. The Higgs field gives the quarks their own fundamental masses, but quantum chromodynamics builds most of the mass of protons and neutrons from energy. Because the strong interaction becomes intense at low energies, ordinary perturbation theory is often not enough to describe it accurately. Physicists therefore use a method called lattice quantum chromodynamics. In lattice quantum chromodynamics, space-time is represented as a discrete grid rather than a perfectly continuous background. Quark fields occupy positions on the grid, while gluon fields are represented along the connections between them. Powerful computers then calculate statistical samples of possible field configurations. By combining enormous numbers of these samples, researchers can estimate hadron masses, decay properties, condensates, and other strong interaction effects. These calculations require substantial computing power. They're carried out by collaborations using national supercomputing centres, university facilities, and particle physics laboratories. Research institutions such as the European Centre for Theoretical Studies in Nuclear Physics and related areas support theoretical work connected with quantum chromodynamics. Major national laboratories and international collaborations also contribute computing resources and specialised expertise. The picture that emerges is very different from the idea of one universal, featureless emptiness. The electromagnetic field has its own vacuum behaviour. The electron field contributes another layer. The quark and gluon fields produce a strongly structured ground state with condensates, broken symmetries, and confined energy. There is no single blank vacuum placed beneath every theory. Each interacting field helps shape the lowest energy state of the universe. What appears empty from a distance may therefore contain the silent structure responsible for holding nuclei together and creating most of the mass of ordinary matter. The Higgs field offers one of the clearest examples of why the quantum vacuum is not simply an empty collection of fields resting at zero. According to the standard model of particle physics, the Higgs field extends throughout the observable universe. Even in its lowest energy state, the field has a non-zero value everywhere. Empty space is therefore filled with a persistent quantum field whose presence helps determine the properties of fundamental particles. This is different from the simplest picture of a field. A perfectly calm classical field might be imagined as sitting at zero in every location. Nothing is displaced, nothing is oscillating, and nothing appears to be present. The Higgs field does not behave that way. Its lowest energy condition is not found at zero. Instead, the field naturally settles into a state with a non-zero value. The reason can be understood through the Higgs potential, which describes how the energy of the field depends on its value. In simplified illustrations, this potential is often shown as a shape resembling a shallow circular valley with a raised point in the middle. At the central point, the field value is zero. Yet this position does not represent the lowest possible energy. It is unstable, rather like a ball balanced exactly on top of a rounded hill. Any small disturbance allows the field to move away from the center and settle somewhere in the lower valley surrounding it. Every location around that valley has the same minimum energy, but each corresponds to a different field orientation. This process is called spontaneous symmetry breaking. The word spontaneous does not mean the field makes a conscious choice. No decision is being taken, and no intention is involved. It simply means that the underlying equations possess a symmetry, while the lowest energy state occupied by the field does not display that symmetry in the same way. A familiar comparison is a perfectly balanced pencil standing upright on its point. The arrangement is symmetric in every horizontal direction. No direction is preferred. Once the pencil falls, however, it lies in one particular direction. The laws remain symmetric, but the final state does not. The symmetry has been hidden by the state the system occupies. During the early universe, the Higgs field is thought to have behaved differently because temperatures were extraordinarily high. As the universe expanded and cooled, the field settled into its present non-zero vacuum state. The theoretical mechanism was developed during the early 1960s through the work of several physicists. Peter Higgs and François Englert are the names most commonly associated with it, while Robert Brute, Gerald Guralnick, Carl Hagen, and Tom Kibble made closely related and essential contributions. Their work showed how a field with a non-zero vacuum value could preserve the mathematical consistency of the electroweak theory, while allowing some force-carrying particles to possess mass. The electroweak theory unifies the electromagnetic interaction with the weak interaction at sufficiently high energies. The weak interaction is responsible for processes including certain forms of radioactive decay and the reactions that allow the sun to convert hydrogen into helium. The electromagnetic interaction is carried by the photon, while the weak interaction is carried by the W bosons and the Z boson. Without the Higgs mechanism, the mathematical symmetry of the theory would require these force carriers to behave as massless particles. The photon is indeed massless, but the W and Z bosons are extremely massive. The W bosons have masses of roughly 80 billion electron volts, while the Z boson has a mass of about 91 billion electron volts. A proton, by comparison, has a mass of just under 1 billion electron volts. The interaction between the W and Z fields and the non-zero Higgs field gives these bosons their rest masses. The photon interacts with the Higgs field in a different way and remains massless. Quarks and charged leptons also acquire rest mass through their interactions with the Higgs field. Charged leptons include the electron, the muon, and the tau particle. Different particles couple to the Higgs field with different strengths. A stronger coupling produces a greater mass. The top quark interacts very strongly with the Higgs field and is extremely heavy. The electron couples much more weakly and has a far smaller mass. The Standard Model successfully describes these couplings, but it does not explain why the coupling strengths have the particular values observed in nature. The Higgs mechanism explains how particle masses can arise while preserving the structure of the theory, but not why one particle is assigned one strength and another particle a very different one. It is also important not to say that the Higgs field creates all mass. The Higgs field provides the fundamental rest masses of quarks, charged leptons, and the W and Z bosons. Yet most of the mass found in ordinary matter lies inside protons and neutrons. A proton contains 3 main quarks, but their individual Higgs-generated masses account for only a small fraction of the proton's total mass. Most of it comes from quantum chromodynamics. The motion of quarks, the energy stored in gluon fields, and the intense dynamics of the strong interaction all contribute to the mass of the proton. The same is true for the neutron. Since most visible matter is made from protons and neutrons, much of the mass in a chair, a mountain, or a human body comes from strong interaction energy, rather than directly from the Higgs field. The Higgs field remains essential, however. Without it, electrons would be massless, atoms would not possess their familiar structure, and the weak force would behave very differently. The universe would not resemble the one we observe. The Higgs boson is not the same thing as the Higgs field. The field is the continuous quantum entity extending throughout space. The boson is a detectable excitation of that field. A useful comparison is the relationship between the electromagnetic field and a photon. The electromagnetic field exists throughout space, while a photon is one quantum excitation of it. In the same way, the Higgs boson is a ripple or excitation in the Higgs field. For decades, the Higgs mechanism remained a successful but incomplete part of the Standard Model, because the associated boson had not been directly observed. That changed in 2012 at the Large Hadron Collider, operated by the European Organisation for Nuclear Research near Geneva. The Large Hadron Collider accelerated protons to extremely high energies and brought them into collision. In a tiny fraction of those collisions, enough energy was concentrated to produce a Higgs boson. The particle decayed almost immediately into other particles, so it could not be observed directly as a stable object. Instead, researchers reconstructed its presence from the energies, directions, and identities of its decay products. The ATLAS collaboration and the compact muon solenoid collaboration independently reported evidence for a new particle with a mass of around 125 billion electron volts. Further measurements showed that its properties were consistent with the Higgs boson predicted by the Standard Model. The discovery provided powerful evidence that the Higgs field is not merely a mathematical convenience. An excitation of the field had been produced and measured. Because the Higgs field has a non-zero value everywhere, it is tempting to imagine particles pushing through it as though moving through syrup. This comparison is misleading. Particles do not continuously lose energy simply because the field fills space. Uniform motion through the Higgs vacuum does not create ordinary drag or friction. There is no preferred state of rest relative to the Higgs field that could be detected as a cosmic headwind. The interaction changes the relationship between a particle's energy, momentum, and rest mass. It does not behave like collisions with molecules in a liquid or gas. A particle moving freely through empty space can therefore continue without slowing down. The Higgs field contributes to what the particle is, not to an ordinary resistance against its motion. This makes the Higgs vacuum especially revealing. Empty space can contain a field whose value is permanently non-zero, whose interactions give fundamental particles mass, and whose excitations can be created in a collider. The vacuum is not simply what remains after all the particles have gone. In the case of the Higgs field, what remains helps decide what those particles are capable of being in the first place. It is natural to imagine that a particle either exists or does not exist. An electron is present in a region of space, or it is not. A photon travels towards a detector, or no photon is there to be found. Quantum field theory makes this picture more delicate. In some situations, the number of particles associated with a quantum field can depend on how an observer is moving, and on the structure of the space-time through which the field extends. This does not mean that reality changes according to personal opinion. It means that the mathematical division between a field's vacuum state and its particle excitations is not always the same for every possible observer. An inertial observer moves at constant velocity. Such an observer may be resting in a chosen frame or travelling steadily in a straight line, but experiences no continuous acceleration. According to Albert Einstein's special theory of relativity, all inertial observers describe the laws of physics in equivalent ways. They may disagree about distances, durations, and whether two separated events occur simultaneously, yet no inertial observer occupies a uniquely correct state of absolute rest. An accelerated observer is different. Acceleration means that velocity changes, either in speed, direction, or both. A person standing on Earth is technically accelerated because the ground prevents them from following the freely falling path that gravity would otherwise produce. A rocket firing its engines provides a clearer example, because its occupants feel a persistent force pressing them against the interior. Quantum fields can appear surprisingly different to observers following these two kinds of motion. Consider an ideal quantum field in flat space-time. An inertial observer describes the field as being in its vacuum state, with no ordinary particles available for a detector to collect. Now imagine another observer accelerating uniformly through the same region. According to quantum field theory, the accelerated observer does not describe the state as an empty vacuum. Instead, that observer perceives a thermal distribution of particles. This prediction is called the Unruh effect. The theoretical foundations were developed through work by Stephen Fulling, Paul Davies, and William Unruh during the 1970s. Fulling studied quantum fields from the perspective of accelerated observers. Davies explored related thermal behaviour, and Unruh presented the effect in a particularly clear physical form. The result is often summarised by saying that an accelerating detector becomes warm in what an inertial observer calls empty space. The temperature depends directly on the acceleration. Greater acceleration corresponds to a higher Unruh temperature. For familiar accelerations, however, the temperature is almost impossibly small. An acceleration comparable with Earth's surface gravity would correspond to a temperature of only around 4 times 10 to the power of negative 20 Kelvin. Written more gently, that is a decimal point followed by 19 zeros before any meaningful digit appears. It is vastly colder than the cosmic microwave background and far beyond ordinary experimental sensitivity. To perceive an Unruh temperature of about 1 Kelvin, an observer would need an acceleration of roughly 10 to the power of 20 meters per second squared. That is about 10 billion times the acceleration experienced near Earth's surface. Uniform acceleration of that magnitude is not something a conventional laboratory detector can politely endure. For this reason, the Unruh effect has not been confirmed through a simple direct experiment in which one detector remains inertial, another accelerates, and the second quietly reports feeling warmer. Researchers have proposed indirect tests and analog systems in which related mathematics may be reproduced, but distinguishing a genuine Unruh signal from other radiation and acceleration effects remains difficult. The effect nevertheless arises naturally from well-established quantum field theory. It reveals that the particle concept is less absolute than everyday intuition suggests. A particle is defined partly through the way a field changes with time. An inertial observer and a uniformly accelerated observer use different notions of time when analysing the same field. As a result, they divide the field into positive frequency and negative frequency components differently. That mathematical division determines which state is called the vacuum and which field excitations are counted as particles. The inertial observer's vacuum can therefore contain a thermal population of particles according to the accelerated observer's description. This does not create a logical contradiction. A detector following the accelerated path can respond as though immersed in thermal radiation, while an inertial analysis accounts for the detector's behaviour through its interaction with the field and the external force maintaining its acceleration. Both descriptions produce consistent predictions for observable events. They organise the physics differently because the observers follow different paths through space-time. The energy detected by the accelerating apparatus does not appear from nowhere. An external agent must continually supply energy to maintain the acceleration. The detector can exchange energy with the field because work is being done on the accelerating system. Once again, the quantum vacuum is not an unlimited power source, hiding behind a clever change of motion. Uniformly accelerated observers are also associated with a boundary known as a Rindler horizon. Imagine a rocket accelerating forever in one direction. Light emitted from sufficiently far behind it may never catch up. The rocket continues gaining speed, always remaining below the speed of light, while the signal loses any chance of reaching the observer. The boundary separating events that can eventually influence the accelerating observer from those that cannot is called a Rindler horizon. This horizon is not a physical wall floating in space. An inertial observer may pass straight through the relevant region without noticing anything unusual. The horizon exists because of the accelerated observer's path and the limits it places on communication. The presence of the horizon divides space-time into regions that are not all accessible to that observer. Information beyond the horizon cannot be included directly in measurements made along the accelerating trajectory. This restriction is closely connected with the thermal character of the Unruh effect. When part of a quantum field becomes inaccessible, the state available to the observer can appear mixed and thermal, even when the complete field occupies a pure vacuum state from a broader perspective. The connection between acceleration, horizons, temperature, and inaccessible information later appears in more dramatic form around black holes. A black hole event horizon also limits which regions can communicate with a distant observer, and quantum fields near such horizons acquire thermal properties. The Unruh effect shows that emptiness cannot always be defined by counting particles, as though they were pebbles scattered through space. Different observers may disagree about the particle content of the same quantum state. They do not disagree about every physical fact. When their complete descriptions are translated properly, they predict compatible detector readings, energy transfers, and observable outcomes. The vacuum is therefore not arbitrary, and reality does not reshape itself according to preference. The field occupies a specific quantum state. Yet the language of particles used to describe that state depends partly on motion, time, accessibility, and measurement. For an inertial observer, a region may be perfectly empty of particles. For an observer accelerating through it, the same region may feel faintly warm. Even emptiness, it seems, depends on how one travels through it. A black hole is one of the clearest places where the quantum vacuum, gravity, and the meaning of a particle become inseparable. To study this properly, physicists use a framework called quantum field theory in curved space-time. In this approach, quantum fields are treated according to quantum theory, while the space-time through which they extend is described as a classical gravitational background. The framework is not yet a complete theory of quantum gravity. Space-time itself is not fully quantized. Even so, quantum field theory in curved space-time reveals effects that cannot be understood using quantum mechanics or general relativity alone. Albert Einstein's general theory of relativity describes gravity not as an ordinary force travelling through a fixed and unchanging arena, but as the curvature of space-time itself. Matter and energy influence that curvature. In turn, curved space-time guides the motion of matter and light. A planet orbiting a star, for example, follows a path through curved space-time rather than being pulled across an otherwise flat background by an invisible Newtonian cord. When a sufficiently massive object collapses into a small enough region, the curvature can become so extreme that a black hole forms. Surrounding the black hole is an event horizon. This is not a solid surface, nor is it a shell of material. It is a causal boundary. Once something passes inside the event horizon, every future directed route available to it leads further inward. Light emitted, there cannot travel back to the distant universe. An observer falling through the horizon of a sufficiently large black hole might notice no sudden barrier at that exact location, but the possibility of returning has already disappeared. Classically, a black hole should absorb matter and radiation without emitting anything of its own. Its horizon allows information and energy to enter but not to escape. Quantum fields alter that conclusion. In 1974, Stephen Hawking calculated how quantum fields behave in the space-time surrounding a forming black hole. He found that a distant observer should detect radiation with an approximately thermal spectrum. A black hole, despite its name, is therefore not perfectly black. The most familiar explanation of Hawking radiation describes pairs of particles appearing near the event horizon. One falls into the black hole while the other escapes. The infalling particle is sometimes said to carry negative energy, reducing the black hole's mass. This image can be useful as an introductory sketch, but it should not be treated as a literal account of tiny pairs continuously forming at a sharply defined surface. Hawking's original calculation concerns the behaviour of quantum field modes across the changing geometry of a black hole spacetime. The more accurate idea is that the definition of a particle in the distant past does not match the definition used in the distant future. Before the black hole forms, the quantum field can be described in a state containing no particles according to the natural observers of that early region. After the collapse, distant observers divide the field into vacuum and particle states differently. Some of the field modes that began as part of the early vacuum are interpreted later as outgoing particles. The result is a stream of radiation reaching great distances from the black hole. This is related to the broader lesson revealed by the Unruh effect. Particle content is not always an observer-independent inventory. Motion, horizons, and the geometry of space-time influence how a field is divided into particles and vacuum. Hawking radiation has a temperature. For a simple, non-rotating and electrically neutral black hole, the temperature becomes lower as the mass becomes greater. A black hole with the mass of the Sun would have a temperature of roughly 60 billionths of a billionth of a Kelvin. This is vastly colder than the cosmic microwave background, which currently has a temperature of about 2.7 Kelvin. Such a black hole would absorb more radiation from its surroundings than it emitted. Its Hawking glow would be completely overwhelmed by the warmer universe around it. Smaller black holes would be hotter. As a black hole loses mass, its temperature rises, allowing it to radiate more rapidly. In principle, this produces a gradual acceleration of the evaporation process. For astrophysical black holes, however, evaporation is extraordinarily slow. A black hole with roughly the mass of the Sun would require around 10 to the power of 67 years to evaporate under idealized conditions. That is an inconceivably long time compared with the present age of the universe, which is about 14 billion years. Stellar black holes are in no immediate danger of fading away before anyone finishes their evening tea. The energy carried by Hawking radiation must come from somewhere. As radiation escapes, the total mass and energy of the black hole decrease. The black hole therefore evaporates gradually. Energy has not been created from nothing. It has been transferred from the mass of the black hole into the outgoing quantum radiation. Hawking's result also completed an extraordinary connection with the work of Jacob Bekenstein. Before Hawking's calculation, Bekenstein had argued that black holes should possess entropy. Entropy is a measure connected with the number of microscopic arrangements compatible with a system's overall measurable state. Bekenstein proposed that black hole entropy is proportional not to the volume inside the black hole, but to the area of its event horizon. Hawking's discovery of a real temperature made this proposal physically concrete. If a black hole has temperature and emits thermal radiation, then it belongs within the laws of thermodynamics. The resulting Bekenstein-Hawking entropy is proportional to the horizon area measured in units related to the Planck length. For an astrophysical black hole, the entropy is enormous, far exceeding that of ordinary matter occupying the same region. This relationship between entropy and area later inspired the holographic principle, the possibility that the information contained within a region of space may be represented by degrees of freedom associated with its boundary. Yet Hawking radiation also creates a serious puzzle. Thermal radiation appears to carry very little information about the detailed matter that originally formed the black hole. If the black hole eventually evaporates completely, it seems possible that the information describing everything that fell inside could disappear. Quantum mechanics ordinarily preserves information through the unitary evolution of a quantum state. General relativity, combined with the original semi-classical Hawking calculation, appears to threaten that principle. This conflict is known as the black hole information paradox. Possible solutions include subtle information encoded within the radiation, long-lived remnants, modifications to the horizon, new relationships between space-time and quantum entanglement, or deeper descriptions supplied by a full theory of quantum gravity. No single explanation has yet been confirmed experimentally. Hawking radiation therefore reveals both the power and the limitations of current physics. Quantum field theory in curved space-time predicts that horizons possess temperature, black holes possess entropy, and the vacuum can appear as real radiation to distant observers. At the same time, the fate of information remains unresolved. Around a black hole, empty space is no longer merely the quiet ground state of a field. It becomes a meeting place for quantum theory, gravity, thermodynamics, horizons, and information. And in that meeting, the vacuum begins to expose the edges of everything physics currently knows. The phrase creating particles from the vacuum can sound as though matter simply appears from nothing. In quantum field theory, that is not what happens. Real particles can be produced from an initial vacuum state, but only when physical conditions supply energy to the field. A sufficiently strong electric field, a rapidly changing boundary, an energetic collision, or an evolving space-time can disturb a quantum field and leave it in a state containing detectable particles. The vacuum is therefore not an empty box filled with hidden objects waiting to be released. It is the lowest energy state of the field under a particular set of conditions. When those conditions change, energy can be transferred into the field, creating genuine excitations. One of the clearest theoretical examples is the Schwinger effect, named after Julian Schwinger. An electron and a positron have equal mass and opposite electric charge. Producing the pair requires enough energy to provide both particles with their rest mass, as well as any motion they possess after creation. An extremely intense electric field can provide that energy. In the quantum description, the electric field changes the possible energy states of the electron field. If the field is sufficiently strong, electron and positron pairs can be produced. The electron is accelerated in one direction, while the positively charged positron moves in the other. The energy has not appeared from nowhere. It comes from the electric field itself. As pairs are created and accelerated, energy stored in the external field is converted into particle mass and motion. The critical electric field associated with efficient pair production is unimaginably large. It is roughly 1 billion volts across a distance of 1 meter. This is far beyond the strength of ordinary laboratory electric fields. Attempting to place such a voltage across familiar equipment would produce a variety of dramatic electrical failures long before the ideal Schwinger conditions were reached. Modern high-intensity lasers can create extraordinarily strong electromagnetic fields, but a clear direct observation of the pure Schwinger effect remains challenging. Researchers investigate combinations of powerful laser pulses, energetic particle beams, and rapidly varying fields that may enhance the probability of pair creation. Particle production through strong fields is already familiar in other forms. High-energy photons passing close to an atomic nucleus can produce an electron and a positron, provided that energy and momentum are conserved. The nearby nucleus helps absorb the required recoil. The Schwinger effect is distinctive because the energy is supplied directly by a sufficiently intense electric field, rather than by a single incoming photon. Changing boundaries can also produce particles. This static Casimir effect involves a force caused by differences between quantum field configurations around closely spaced surfaces. In the dynamical Casimir effect, the boundary conditions themselves change rapidly. Imagine a mirror moving back and forth. The electromagnetic field must continually adjust to the mirror's changing position. If the movement is sufficiently rapid, the field may be driven away from its vacuum state, leaving behind real photons. Moving an ordinary mirror fast enough is not practical. Instead, experiments can alter the effective electrical boundary seen by a field. Researchers have used superconducting quantum interference devices connected to microwave circuits. A superconducting quantum interference device can change the electrical properties of a circuit extremely quickly when controlled by an external signal. From the perspective of the microwave field inside the circuit, the effective boundary appears to move at a substantial fraction of the speed of light, even though no physical mirror is racing through the laboratory. Experiments have measured microwave radiation with properties consistent with photon creation through the dynamical Casimir effect. The observed photons begin as excitations produced from a state that was initially close to the vacuum. Once again, the energy source is not mysterious. External equipment drives the rapid change in the circuit. Energy from that driving signal is transferred into the electromagnetic field and emerges as photons. The vacuum does not donate the energy. It provides the initial quantum state from which the driven system evolves. A similar principle can operate on a cosmic scale. In an expanding universe, the geometry of space-time changes with time. Quantum field modes that once had one wavelength and frequency can be stretched as space expands. If the expansion is sufficiently rapid, or the geometry changes in the appropriate way, a state that initially appears to contain no particles may later be described as containing them. This phenomenon is called cosmological particle creation. The effect is closely related to Hawking radiation and the Unruh effect. In each case, the division between vacuum and particles depends on the behaviour of the field, the observer, and the surrounding space-time. During the early universe, expansion may have amplified quantum field disturbances and produced particles. In models of cosmic inflation, the rapid stretching of space-time can transform microscopic quantum fluctuations into much larger field variations. When inflation ends, the energy associated with the field driving the accelerated expansion must be transferred into ordinary particles and radiation. This proposed process is known as reheating. Reheating would have filled the young universe with a hot mixture of particles, allowing later processes to produce atomic nuclei, atoms, stars, planets, and eventually listeners quietly considering where everything came from. The detailed physics of inflation and reheating remains uncertain, but the general mechanism illustrates an important point. A changing space-time can transfer energy into quantum fields and alter what later observers identify as particles. Real particles must be distinguished from virtual particles. A real particle can travel to a detector and leave a measurable signal. It obeys the appropriate relationship between its energy, momentum, and mass. An electron may produce a track in a particle detector. A photon may be absorbed by an atom or register in a light sensor. Virtual particles are internal mathematical contributions used in perturbative calculations. They are not directly detected objects emerging temporarily from the vacuum, and they do not represent an independent supply of energy. Strong field pair production, the dynamical Casimir effect, and cosmological particle creation All involve real quantum excitations, yet each has an identifiable physical source. The Schwinger effect draws energy from an electric field. The dynamical Casimir effect draws energy from the mechanism changing the boundary. Cosmological particle creation draws upon an evolving gravitational or field background. A collision can convert motion into particles. An accelerating detector must be driven by an external force. A black hole loses mass as Hawking radiation carries energy away. The recurring principle is not that empty space creates something from nothing. It is that quantum fields can transform energy from one form into another. Fields, boundaries, acceleration, and space-time geometry determine which state counts as the vacuum. When those conditions change, the old vacuum may no longer be the lowest energy state appropriate to the new situation. What began as quiet can then contain detectable particles. The quantum vacuum is not an inexhaustible fuel source. It is more subtle than that. It is a physical state capable of responding when the universe changes around it, converting supplied energy into the particles from which the visible world is made. Empty space may influence not only atoms and particles, but the expansion of the universe itself. In Albert Einstein's general theory of relativity, gravity is described as the curvature of space-time produced by matter and energy. Soon after developing the theory, Einstein realized that his equations could include an additional term known as the cosmological constant. The cosmological constant behaves as though space contains a uniform energy density. Unlike ordinary matter, which becomes more dilute as the universe expands, a true cosmological constant remains the same everywhere and at all times. This gives it an unusual gravitational effect. Ordinary matter has positive energy density and negligible pressure on cosmic scales. Its gravity tends to slow expansion by drawing matter together. Constant vacuum energy also has positive energy density, but it is associated with negative pressure. Negative pressure does not mean suction in the everyday sense. It is a property of the relationship between energy, pressure, and space-time in general relativity. For a constant vacuum energy, the pressure is equal in magnitude and opposite in sign to the energy density. This combination can cause the expansion of the universe to accelerate. Einstein originally introduced the cosmological constant while attempting to construct a static model of the universe. At the time, the prevailing assumption was that the universe was eternal and largely unchanging on the grandest scales. Without an additional term, Einstein's equation suggested that a universe filled with matter would not remain perfectly static. Gravity would cause it to contract, or it would already need to be expanding. The cosmological constant allowed Einstein to balance the attractive influence of matter. The proposed static arrangement was unstable, however, and observations later showed that the universe is expanding. During the late 1920s, observations by Edwin Hubble and work by Georges Lemaitre helped establish that distant galaxies are generally receding from us, and that more distant galaxies tend to recede faster. For much of the 20th century, physicists expected gravity to slow this expansion. The central question seemed to be whether the universe would continue expanding forever, or eventually reverse into contraction. The answer became more surprising during the late 1990s. Two international research collaborations were studying distant Type I supernovae. These stellar explosions occur when a white dwarf undergoes a thermonuclear disruption, either through interaction with a companion star or through the merger of compact objects. Type I. A supernovae are useful because their intrinsic brightness can be standardized. By comparing how bright they appear with how bright they are expected to be, astronomers can estimate their distances. Their spectra also reveal how much the universe has expanded while their light was travelling towards Earth. The Supernova Cosmology Project, led by Saul Perlmutter and the High-Z Supernova Search Team, associated with Brian Schmidt and Adam Rees, found that distant supernovae appeared dimmer than expected in a steadily slowing universe. The most consistent interpretation was that the expansion of the universe had begun accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees later received the Nobel Prize in Physics for this discovery. The name dark energy was introduced for the unknown component responsible for the acceleration. It is called dark not because it is literally black, but because its underlying nature remains hidden. Dark energy does not gather visibly into stars or galaxies. It appears to be distributed extremely smoothly across space, and becomes important mainly across the largest cosmic distances. The simplest explanation is that dark energy is a cosmological constant. In that interpretation, empty space possesses a small, constant energy density that does not dilute as the universe expands. This leads to a curious consequence. As the universe grows, more volume of space exists, and the total amount of vacuum energy within that volume increases. This does not violate energy conservation in any simple local sense because defining total energy in an expanding universe is more subtle than in an unchanging background. The standard cosmological model is known as the lambda cold dark matter model. Lambda is the symbol traditionally used for the cosmological constant, although in spoken explanations it is clearer simply to call it the cosmological constant. Cold dark matter refers to non-luminous matter moving slowly compared with the speed of light when cosmic structures began forming. The model combines the cosmological constant, cold dark matter, ordinary atomic matter, radiation, and general relativity. With a relatively small set of parameters, it describes a remarkable range of observations. These include the large-scale distribution of galaxies, the expansion history of the universe, gravitational lensing, the abundance of light elements, and the pattern of temperature variations in the cosmic microwave background. Measurements by the Planck satellite have provided detailed maps of the cosmic microwave background. The Dark Energy Survey has studied hundreds of millions of galaxies and thousands of supernovae. The European Space Agency's Euclid mission is mapping the geometry and growth of cosmic structure across billions of light-years. Other projects use baryon acoustic oscillations, galaxy clusters, weak gravitational lensing, and supernova distances to test whether dark energy behaves exactly like a cosmological constant or changes over time. Within the standard model, dark energy accounts for roughly 2/3 of the total cosmic energy budget. Dark matter contributes a little over 1/4, while ordinary matter makes up only around 1/20. These proportions are inferred from combined observations rather than obtained by simply counting visible objects. The cosmological constant fits existing evidence extremely well. Yet a good mathematical fit does not reveal the microscopic identity of dark energy. Quantum field theory suggests that fields in their vacuum states can contribute energy. General relativity suggests that a uniform energy density could accelerate cosmic expansion. It is therefore tempting to identify dark energy directly with quantum vacuum energy. That connection is plausible, but it is not experimentally proven. The quantum vacuum contains contributions associated with electromagnetic fields, quark and gluon fields, the Higgs field, and other quantum systems. Straightforward estimates of those contributions generally produce values enormously larger than the energy density inferred from cosmic acceleration. The observed dark energy density is astonishingly small by particle physics standards. It corresponds to only a few billionths of a billionth of a billionth of a kilogram of mass equivalent in each cubic meter of space. That is almost nothing locally. Yet because it appears to fill the entire universe, its cumulative effect dominates the expansion across vast distances. Physics is therefore left with a difficult balance to explain. The vacuum energy is not exactly zero if the cosmological constant interpretation is correct. But it is also far smaller than many quantum calculations seem to suggest. Dark energy may be constant vacuum energy. It may arise from a slowly evolving field, sometimes called quintessence. It may point towards a modification of gravity on cosmic scales, or it may reflect physics not yet recognized. For now, the simplest model remains remarkably successful. The expansion of the universe is accelerating, and the cause behaves as though empty space possesses a faint and persistent energy of its own. Across a laboratory chamber, that energy is imperceptible. Across the whole observable universe, it may determine the fate of everything. The cosmological constant problem is sometimes called the worst prediction in physics. The name is dramatic, but the difficulty behind it is real. Quantum field theory suggests that empty space should possess energy. Cosmological observations suggest that something resembling a small vacuum energy may be driving the accelerated expansion of the universe. The problem is that the theoretical expectations and the observed value seem to disagree by an extraordinary amount. A simple estimate begins with a 0-point energy of quantum fields. Every allowed mode of a quantum field behaves mathematically like a quantum oscillator, and every oscillator possesses a lowest permitted energy. A field contains modes with many different wavelengths and frequencies. If their ground state energies are added together, the total rises rapidly as shorter wavelengths and higher energies are included. Without any upper limit, the sum becomes infinite. Physicists can instead introduce a temporary maximum energy known as a cutoff. This says, in effect, that the calculation will include field modes only up to a chosen energy scale. The resulting answer is finite, but it can still be immense. If the cutoff is placed near the Planck scale, where quantum gravity is expected to become important, the estimated vacuum energy density can exceed the observed dark energy density by roughly 120 orders of magnitude. An order of magnitude represents a factor of 10. A disagreement of 120 orders of magnitude, therefore, means a factor written as 1 followed by around 120 zeros. This familiar figure should be treated with care. It is not a single exact prediction produced by a complete theory. The size of the mismatch depends on which fields are counted, which cutoff is chosen, how the calculation is organized, and what assumptions are made about unknown high-energy physics. Even less extreme and more conservative estimates still create an enormous problem. The precise number may vary, but the disagreement remains far too large to dismiss as a minor correction. 0-point energies are only part of the difficulty. The quantum chromodynamic vacuum has its own structured ground state, including contributions associated with quark and gluon condensates. The energy scale involved in the strong interaction is vastly greater than the vacuum energy inferred from cosmic acceleration. The Higgs field also contributes to the problem. Its potential changes when electroweak symmetry is broken, and the field settles into its present non-zero vacuum state. The associated shift in energy is again enormously larger than the observed cosmological constant. Other phase transitions in the early universe may have changed vacuum energies as fields move between different states. Each contribution might be positive or negative depending on the theory and convention. General relativity appears to respond to their combined total. The mystery is therefore not simply why one calculated number happens to be too large. It is why several individually enormous contributions seem to combine into a final value that is extremely close to zero, but not exactly zero. To reproduce the observed cosmic acceleration, these terms would need to cancel with an almost unbelievable degree of precision. It is rather like adding several vast numbers together and somehow being left with the price of a cup of tea. This difficulty is known as the old cosmological constant problem. It asks why the vacuum energy is not enormous. There is also a related question called the coincidence problem. The density of ordinary matter decreases as the universe expands because the same amount of matter becomes spread through a larger volume. The density associated with a true cosmological constant remains unchanged. In the early universe, matter was much denser than dark energy and dominated cosmic evolution. In the distant future, a constant dark energy component would dominate overwhelmingly. Yet humanity happens to exist during the comparatively brief cosmic era, when the densities of matter and dark energy are of roughly similar magnitude. The coincidence problem asks why dark energy becomes important around the present period of cosmic history, rather than vastly earlier or later, There may be an underlying physical explanation, an observational selection effect, or simply a coincidence. At present, no answer is confirmed. One proposed solution involves supersymmetry. Supersymmetry is a theoretical relationship between two broad classes of quantum particles. Fermions include matter particles such as electrons and quarks. Bosons include force-carrying particles such as photons and gluons. In an exactly supersymmetric theory, every bosonic contribution would be paired with a corresponding fermionic contribution. Their zero-point energies would have opposite signs and could cancel. This makes supersymmetry attractive in discussions of vacuum energy. Unfortunately, the particles of the standard model do not appear in perfectly matched boson and fermion pairs. If supersymmetry exists in nature, it must be broken at accessible energies. The hypothetical partner particles would therefore be heavier than their familiar counterparts. Particle searches at the Large Hadron Collider have not found confirmed evidence of supersymmetric particles. Broken supersymmetry would also leave residual vacuum energy contributions that could still be vastly larger than the observed value. Supersymmetry may improve parts of the theoretical picture, but it does not automatically solve the cosmological constant problem. Another line of thought combines anthropic reasoning with the proposed landscape of string theory. Some versions of string theory appear to allow an enormous number of possible vacuum states. Different regions of a much larger cosmos might settle into different states, each with its own particle properties and cosmological constant. Most vacuum values might produce universes that expand too quickly for galaxies to form or collapse too rapidly, for complex structures to survive. Observers would naturally find themselves only in regions where the vacuum energy permits stars, planets, and long-lived cosmic structure. This is the anthropic argument. The observed value may not be selected by a unique fundamental law, but by the requirement that observers can exist to measure it. The idea is associated with discussions by physicists including Steven Weinberg, Leonard Susskind, and others working on cosmology and string theory. Anthropic reasoning remains deeply debated. The proposed string landscape has not been experimentally mapped. Other vacuum regions have not been observed, and the argument may not provide the kind of direct mechanical explanation many physicists would prefer. Other proposals include a slowly changing dark energy field, modifications of gravity, unknown symmetries, dynamical adjustment mechanisms, and new relationships between space-time and quantum information. None has yet resolved the problem decisively. The cosmological constant problem is therefore not a disagreement caused by one misplaced decimal point. It exposes a deep tension between two remarkably successful frameworks. Quantum field theory accurately describes particles and three fundamental interactions. General relativity accurately describes gravity, space-time, and the large-scale universe. When quantum field theory estimates the energy of empty space, and general relativity is asked how that energy should curve space-time, the combined answer appears catastrophically wrong. Some hidden cancellation, deeper principle, or new description of gravity and the vacuum seems to be missing. Empty space appears to contain a tiny positive energy. Physics can measure its cosmic effect with increasing precision. Explaining why it has that value remains one of the quietest and largest mysteries in the universe. The quantum vacuum found throughout the universe today may not be the same state that existed during its earliest moments. As the universe expanded, it also cooled. Temperatures that were once unimaginably high gradually fell, and the quantum fields filling space could settle into new configurations. The vacuum itself may therefore have changed as the young universe passed through a series of physical transitions. A familiar comparison is water freezing. Liquid water and solid ice are made from the same molecules, but those molecules are arranged differently. Above the freezing point, liquid water is the more stable state. Below it, an ordered crystal structure becomes energetically favourable. This change is called a phase transition. Quantum fields can undergo phase transitions as well, although the transition does not involve droplets or crystals. Instead, the field moves from one configuration to another because the lowest energy state available to it changes as temperature falls. One important example is electroweak symmetry breaking. At the extremely high temperatures of the early universe, the electromagnetic interaction and the weak interaction behaved as parts of a unified electroweak force. The Higgs field did not occupy the same non-zero vacuum state found throughout space today. As expansion cooled the universe, the Higgs field settled into a new lowest energy configuration with a persistent non-zero value. This transition separated the familiar electromagnetic and weak behaviours and gave rest mass to the W bosons, Z boson, quarks, and charged leptons through their interactions with the Higgs field. The fundamental laws had not been replaced, but their visible expression changed because the vacuum state changed. The properties of particles in the hot early universe may therefore have differed from their present properties. Particles that are now massive could behave effectively as massless excitations at sufficiently high temperatures. Forces that now appear distinct may have been joined within a more symmetrical description. As the universe cooled further, other transitions connected with the strong interaction may also have altered the organisation of quark and gluon fields. The vacuum was not simply an unchanging container in which cosmic history occurred, it participated in that history. An even earlier proposed event is cosmic inflation. Inflation is the idea that the universe passed through a brief period of extraordinarily rapid expansion. Important versions of the theory were developed through work by Alan Guth, Alexei Starobinsky, Andrei Linde, and other physicists during the late 1970s and early 1980s. The expansion would have been much faster than the later growth described by ordinary radiation and matter. This does not mean objects travelled locally through space faster than light. Rather, the distance between widely separated regions increased because space-time itself expanded. Inflation is often modelled using a scalar field. A scalar field assigns a numerical value to every point in space without also assigning a direction. In these models, the field begins in a high-energy state and changes only slowly for a short period. Its energy behaves approximately like vacuum energy, with negative pressure that drives accelerated expansion. The proposed field is commonly called the inflaton, although its actual identity is unknown. It may represent a fundamental field not yet discovered, a combination of fields, or an effective description of deeper physics. Inflation was introduced partly to explain several puzzling features of the observable universe. It can account for why distant regions possess nearly the same temperature, why space appears extremely close to geometrically flat on large scales, and why unwanted relics predicted by some early theories are not commonly observed. Its most remarkable consequence may involve quantum fluctuations. Even while a field occupies a vacuum-like state, quantum uncertainty remains. During inflation, tiny field fluctuations could have been stretched rapidly across immense distances. Modes that began at microscopic scales would expand beyond the effective horizon of the inflationary universe. Their patterns could then become preserved as small variations in density and space-time curvature. After inflation ended, those variations would remain as slightly denser and slightly thinner regions within the hot early universe. Gravity would slowly amplify them. Denser regions would attract more matter, eventually helping to form galaxies, galaxy clusters, and the vast cosmic web. The large-scale structure visible today may therefore have grown from quantum fluctuations that once belonged to an early vacuum-like state. Evidence for these primordial patterns appears in the cosmic microwave background, the faint radiation released when the universe became transparent roughly 380,000 years after the hot early phase began. The Cosmic Background Explorer satellite first detected small temperature variations across this radiation. The Wilkinson microwave anisotropy probe later mapped them in much greater detail. The Planck satellite produced even more precise measurements of their scale, distribution, and statistical properties. The observed fluctuations are close to the nearly scale-invariant pattern predicted by many simple inflationary models. They are also predominantly adiabatic, meaning the different components of the early cosmic material vary together in the expected way. These successes provide strong support for the broad idea of an inflationary period, yet the detailed theory remains uncertain. Physicists do not know which field caused inflation, exactly how it began, how long it lasted, or precisely how its energy was transferred into particles and radiation afterward. Many different inflationary models can reproduce the main observations. Some make additional predictions, including particular patterns of primordial gravitational waves, but those signals have not yet been confirmed. Inflation is therefore more than speculation, but less than a completed description of the earliest universe. Its broad framework explains several important observations with striking economy. Its underlying mechanism remains hidden. What can be said with confidence is that the present universe contains patterns whose earliest known origins appear quantum mechanical. Galaxies, stars, planets, and enormous cosmic voids may all trace their ancestry to tiny variations in fields during an ancient vacuum-like state. The quietest quantum behaviour at the smallest scales may have been stretched across the sky, leaving a faint blueprint from which the visible universe eventually grew. The quantum vacuum may be the lowest energy state available to the fields of nature, but that does not automatically mean it is the lowest state that could ever exist. A field can occupy an absolutely stable ground state, with no lower energy configuration available anywhere. It can also occupy a metastable state, which remains unchanged for an extremely long time even though a deeper state is theoretically possible. A useful comparison is a ball resting in a shallow valley. Small disturbances may cause it to roll slightly, but it always returns to the bottom. From its immediate surroundings, the ball appears stable. Far away, however, there may be a deeper valley separated from the first by a hill. The ball is secure against ordinary pushes, yet it is not sitting at the lowest point in the entire landscape. In field theory, this kind of higher valley is called a false vacuum. It is a local minimum of energy rather than the absolute minimum. The word false does not mean imaginary. A false vacuum can be physically real and remain stable for periods vastly longer than the age of the universe. It is false only in the sense that a still lower energy state may exist. Classically, a field trapped in such a minimum would need enough energy to rise over the barrier separating it from the deeper state. Quantum theory permits another possibility. Through quantum tunneling, a system can move into a state that classical physics would not allow it to reach directly. The field does not climb over the barrier in the ordinary sense. Instead, the quantum transition has a small but non-zero probability of occurring. Theoretical work by Sidney Coleman explored how this process could cause a false vacuum to decay in quantum field theory. Coleman and Frank DeLucia later extended the analysis to include the effects of curved space-time and gravity. A vacuum transition would not necessarily happen everywhere at once. It could begin through the nucleation of a tiny region, or bubble, in which the field has shifted into the lower energy vacuum. At first, the bubble would be microscopic. If the new vacuum were truly more stable, the bubble could expand rapidly, with its boundary moving outward at close to the speed of light. Inside the bubble, the values of fundamental fields would differ from those in the surrounding universe. This could change particle masses, interaction strengths, and perhaps the kinds of stable matter that could exist. The phrase vacuum decay therefore describes more than empty space, becoming slightly emptier. It would mean the underlying physical state of space changing into a different configuration. The Higgs field has made this question especially important. Measurements place the Higgs boson mass at roughly 125 billion electron volts. The top quark has a mass of roughly 173 billion electron volts, although its precise theoretical interpretation and experimental value require considerable care. When these measurements are inserted into calculations based on the standard model, The present Higgs vacuum appears to lie close to the boundary between absolute stability and metastability. Some calculations suggest that the Higgs potential may eventually bend downward again at energies far beyond those directly reached in experiments. If so, the present vacuum could be a very long-lived false vacuum. This conclusion is not perfectly settled. It depends sensitively on the exact top quark mass, the Higgs boson mass, the strength of the strong interaction, and the methods used to extend the standard model to extremely high energies. Even tiny changes in those inputs can shift the result. Unknown physics beyond the standard model could also alter the shape of the Higgs potential and make the vacuum more stable or less stable than current calculations suggest. Metastability should not be confused with immediate danger. Theoretical estimates generally suggest that, even if the present vacuum is metastable, its expected lifetime is vastly longer than the current age of the universe. The universe is about 14 billion years old. Estimated vacuum decay timescales can exceed that age by an almost incomprehensible number of orders of magnitude. A transition could be possible in principle, while remaining so improbable that it is effectively irrelevant throughout any familiar cosmic future. Particle accelerators do not create a credible vacuum decay threat. The Large Hadron Collider produces extremely energetic collisions, but nature has been performing collisions of comparable and greater energy for billions of years. Cosmic rays strike Earth, the Sun, neutron stars, and other astronomical bodies at energies exceeding those reached by human accelerators. If such collisions could readily trigger vacuum decay, the universe would already have provided countless opportunities. Safety assessments conducted before operation of the Large Hadron Collider considered these questions in detail. The continued existence of Earth and long-lived astronomical objects exposed to natural cosmic rays provides strong evidence that collider experiments do not pose this danger. The possibility of vacuum decay is therefore not a warning about an approaching catastrophe. It is a theoretical question about the deeper structure of the laws governing fields. The vacuum may be absolutely stable. It may be metastable but unimaginably long-lived. Or a deeper theory may change the entire picture. What seems like permanent empty space may be one state within a larger landscape of possibilities. Yet for every practical purpose, the vacuum around us appears remarkably secure. Nature may leave the door to another state slightly open in the mathematics, but it has placed that door at an almost unreachable distance. The quantum vacuum is no longer understood as a simple absence. It is the lowest energy state available to quantum fields. It can contain no ordinary particles and still possess correlations, uncertainty, structure, and measurable physical effects. The vacuum influences how atoms emit light. It contributes to the Lamb shift in hydrogen, alters the electron's magnetic moment, modifies the effective strength of electric charge, and helps produce the Casimir force between closely spaced surfaces. These are not merely philosophical possibilities. They are connected with experiments whose results agree closely with the predictions of quantum electrodynamics. The Lamb shift has been measured through precision spectroscopy. Casimir forces have been detected between carefully prepared surfaces. Vacuum polarization contributes to the observed running of the electromagnetic coupling. Quantum corrections to the electron's magnetic moment have been tested to extraordinary accuracy. Together, these measurements show that the vacuum is physically consequential. Other effects remain more difficult to test directly. The Unruh effect predicts that a uniformly accelerating observer should perceive thermal particles, where an inertial observer describes a vacuum. The mathematics fits naturally within quantum field theory, but the required accelerations are so immense that a simple direct laboratory confirmation remains beyond present capabilities. Hawking radiation arises from closely related ideas involving quantum fields, horizons, and curved space-time. Its theoretical foundation is strong, yet the radiation from known astrophysical black holes would be far too faint and cold to detect against the surrounding universe. The distinction between established measurement and well-motivated prediction matters. The quantum vacuum is remarkable enough without treating every elegant theoretical possibility as an observed fact. Its greatest unresolved difficulty may be the cosmological constant problem. Quantum field theory associates ground state energies with fields. General relativity treats energy and pressure as sources of space-time curvature. Yet straightforward theoretical estimates of vacuum energy appear enormously larger than the small value inferred from the accelerating expansion of the universe. No accepted explanation shows why the various vacuum contributions of particle physics should combine into such a tiny positive result. This problem lies at the meeting point of particle physics, cosmology, and gravity. It suggests that at least one part of the present description remains incomplete. Quantum field theory successfully describes matter and 3 of the 4 known fundamental interactions. Quantum electrodynamics describes electromagnetism. Quantum chromodynamics describes the strong interaction. Electroweak theory unifies electromagnetism with the weak interaction at high energies. Gravity remains outside this quantum framework. Albert Einstein's general theory of relativity describes gravity with extraordinary success as the curvature of space-time. It predicts black holes, gravitational waves, the bending of light, and the expansion of the universe. Yet general relativity treats space-time as a smooth classical geometry. Quantum field theory describes matter through uncertain and quantized fields. Under extreme conditions, such as the centres of black holes or the earliest moments of the universe, both descriptions are needed at once. A complete quantum theory of gravity has not yet been confirmed. String theory proposes that fundamental particles arise from different vibrational states of extremely small strings. In many versions, gravity appears naturally through a quantum excitation associated with the graviton. The theory also requires additional spatial dimensions and permits a vast range of possible vacuum configurations. It provides powerful mathematical connections, but no direct experimental evidence has yet established that strings are the fundamental ingredients of nature. Loop quantum gravity takes a different approach. It attempts to quantize space-time geometry itself, suggesting that areas and volumes may possess discrete quantum properties at extremely small scales. Causal set theory proposes that space-time may emerge from a discrete network of elementary events connected by causal order. Asymptotic safety explores whether gravity can remain mathematically consistent at arbitrarily high energies by approaching a particular fixed pattern of interaction strengths. Holographic ideas suggest that the information describing a volume of space may be represented by degrees of freedom associated with a lower dimensional boundary. None of these approaches has been experimentally confirmed as the final theory of quantum gravity. The holographic principle grew from the study of black hole entropy. Gerard 't Hooft and Leonard Susskind argued that the information contained within a region might be encoded on its boundary rather than distributed independently throughout its volume. Juan Maldacena later discovered a precise mathematical relationship known as the anti-de Sitter conformal field theory correspondence. This correspondence connects a gravitational theory and a higher dimensional anti-de Sitter spacetime with a quantum field theory defined on its lower dimensional boundary. The result is one of the clearest examples of spacetime and gravity emerging from a theory that does not contain gravity in the same form. Our observable universe is not known to be anti-de Sitter space, so the correspondence cannot simply be applied as a complete description of reality. Even so, it has transformed research into black holes, quantum information, strongly interacting fields, and the possible emergence of space-time. The idea that space-time may be emergent is especially profound. Quantum fields are normally imagined as existing within space and changing through time. But if space-time itself arises from deeper quantum relationships, then fields may not ultimately live on a fundamental background. Space could emerge from patterns of quantum entanglement. Time might arise from change within a more basic structure. Geometry could reflect relationships between information rather than exist as an independent container. These possibilities remain speculative, but they suggest that the current words field, particle, vacuum, space, and time may be approximations belonging to one level of description. A deeper theory could preserve their successful predictions while redefining what they mean. Future progress may come from many directions. Particle colliders can search for unknown particles, hidden symmetries, or departures from the standard model. Precision atomic experiments can test quantum electrodynamics and fundamental constants with ever greater sensitivity. Gravitational wave observatories can examine black hole mergers and the structure of strong gravitational fields. Cosmological surveys can measure dark energy, galaxy formation, gravitational lensing, and the expansion history of the universe. Experiments involving quantum sensors, interferometers, clocks, cold atoms, and high-intensity lasers may reveal effects too faint for earlier instruments. No single observation is guaranteed to uncover the deeper nature of the vacuum. Scientific understanding often advances through many small deviations, constraints, and increasingly precise measurements. What is already clear is that empty space is not where physics disappears. It is where fields settle into their quietest state, where quantum correlations remain without ordinary particles, where boundaries can produce forces, and where gravity exposes unresolved tensions between the smallest and largest scales. The vacuum appears empty only when judged by the absence of visible matter. Look more carefully, and it becomes one of the places where the deepest laws of nature are most clearly revealed. Empty space is never truly empty, because even when no ordinary particles can be detected, the quantum fields of nature remain. The journey to that conclusion began with classical ideas of the void, then changed through Michael Faraday's fields, James Clerk Maxwell's electromagnetism, Max Planck's quantization, Albert Einstein's relativity, Paul Dirac's quantum theory, and the eventual development of quantum field theory. A region containing very little matter is not the same as the quantum vacuum. The quantum vacuum is the lowest energy state of interacting fields. It carries zero-point properties and measurable correlations, but it is not literally crowded with real particles continuously appearing from nothing and borrowing energy without consequence. Its influence can be seen in spontaneous emission, atomic energy shifts, vacuum polarization, the electron's magnetic moment, Casimir forces, and high-energy particle interactions. The quantum chromodynamic vacuum helps shape the strong force, while the non-zero Higgs field contributes to the masses of fundamental particles. The Unruh effect, Hawking radiation, and cosmological particle creation reveal that particles and emptiness can depend on acceleration, horizons, and space-time itself. Dark energy may reflect vacuum energy, yet the cosmological constant problem shows that gravity's response to the vacuum remains deeply unexplained. Inflation, early universe phase transitions, and possible vacuum metastability suggest that the vacuum may also have changed across cosmic history, although important details remain uncertain. What appears to be nothing is therefore the quiet ground state of everything known. It is not crowded in the ordinary sense, but it is structured, responsive, measurable, and inseparable from the laws that allow matter, light, space, and time to exist.